What's up, guys? So today we're continuing the trend of exploiting my wife for views. What's up, guys? So today we're going to be taking a look at soldering 0201 components on the Switch motherboard, which she has no idea what that means.
No.
But she's going to figure that out. All set?
Yeah.
With your massive gloves.
With my massive gloves.
So on the back of this motherboard, you can see there's a bunch of small components like in a cluster. Yeah, the biggest one in the middle there. Yeah. So that's behind the SoC of the Switch motherboard.
What's SoC for?
It stands for System on Chip, and it's like this is the SoC there. It's basically the
so that's the back
CPU
of this.
GPU combination.
I see.
So usually, like in a computer, you'll have one chip for like the CPU, and then you'll have a separate chip for the graphics card. So as an example, here's an Asus motherboard. So this chip here, this is the CPU, and this is the GPU, and that is like a combination of those two for the Switch.
See.
So it sort of does both, and probably a few more things than these two would do separately. But yeah, that's what an SoC is.
Nice new mat.
Thank you.
So big.
Yeah, it's great.
You're gonna need new Q-tips.
I have a box of them.
Okay.
Behind like CPUs, GPUs, and SoCs like this, oftentimes there's lots of what are called decoupling capacitors like this. And you can see there's like a bunch of different sizes there that they're not all the same size. So if you zoom in with the microscope, you'll be able to see much better.
I'm in charge of
The microscope?
deck.
Okay, the stream deck?
Yeah,
okay.
yeah.
So I'll switch to the microscope here.
And is it at an angle for a reason?
Yes, I put it at an angle to reduce glare.
Okay.
Because watch this. If I do this, lots of glare. If I just angle it a tiny bit.
Nice. Okay.
So these are the decoupling capacitors behind the SoC.
What's a capacitor?
So a capacitor is like a component that holds a charge, essentially. In this case, they're being used to smooth out like voltage lines and things like that.
So are they all capacitors?
Not all of them. Most of them are capacitors. Some of them are resistors. You see the black ones? So yeah, the black ones
like
are resistors.
This?
Yes, that one, and then the bigger one above it, that's a
Yeah, that
resistor.
one.
But all the other ones that are like beige and stuff, those are all capacitors. And those are all, or most of them are in place for decoupling. When you're working at like really high frequencies or like with really complicated chips like this, you don't want like lots of noise and like ripples in your voltage. So there's a ton of them on here because they sort of all share the load to like smooth things out.
Okay. I'm much better at gauging the distance than I was last time.
Yeah, so you can like grab all of them. These tweezers are like really
What's this?
precise. That is just a test point. So it doesn't do anything. It's literally just a pad used for testing purposes. But
And what about those?
those are footprints of like missing components or components that weren't put on. I don't want to say missing because they purposefully weren't put there. Also, like on PCBs, they want to have like, you know, flexibility sometimes. So they'll like print them with more footprints than they necessarily are going to use. This is really common on most PCBs.
These are trays.
Yeah, all the little squiggly things.
Yeah.
Yeah, those are all traces. Anywhere that's not like dark green, everywhere that is light green.
Oh, like this?
Yeah, that's a trace. So that's actually, if we were to scrape, actually let's scrape that for fun. Grab the grinding pen, which is this. Yeah, this is a donor board, by the way. This is not matter if we ruin this. So just press once, and then just sort of like grind into that a little bit. So you'll see like this is copper underneath here.
Yeah.
See that?
Yeah.
So you can stop if you want, and you can clean it with a Q-tip, and you'll be able to see like there's actually copper underneath.
That looks so big. Smaller than a piece of dust.
Yeah, so you can see how that's like copper underneath there.
And again.
Anakin is currently trying to open the drawer.
What do you think's in there? Oh, it's styrofoam?
Oh, he's gonna eat that.
Stupid cat.
Yeah, it's styrofoam.
Our cat is obsessed with styrofoam.
Okay, so like all of those light green areas have copper underneath it, like that. So you can see like some of them are thicker, some of them are thinner. The one you just did there, that's a ground plane. The like biggest ones are almost always gonna be the ground plane. Then like the other ones that are like near some of those capacitors that are thicker, some of those are going to be ground and some of those are going to be actually voltage rails. Yeah, so those, and then like that's probably ground if I were to guess. But like some of those in there are going to be either ground or a voltage rail. Usually the voltage rails are thicker so they can deliver more power essentially. If you have a resistor there, like one of those black components, take the multimeter probes, which are right here. This is the first time you're ever going to use a multimeter.
Yeah, it is. Is one supposed to be on one side?
No, not necessarily. So if you touch them together, you can see right now it's at like 1 ohm or under 1 ohm. There on the top left of the screen, there's 100 milliohms instead of an ohm. What are you doing? Oh, I see. It's hard to point. It's right here. This is the sweet spot.
Oh. You know where it is. Here.
Yeah, so right there, that's showing like 150-ish milliohms, which is 0.15 of an ohm. So whatever you touch with this, the electricity is going to take the path of least resistance.
This is electricity in, and this is measuring out.
So it depends on what you're doing with your multimeter. So like in resistance mode, your red probe is putting out actually like a really small constant current. Actually, let me actually draw this. I guess we're not doing O201 components today, but maybe we will.
I'm asking too many questions.
Today we're teaching my wife Ohm's law. So this is Ohm's law here. You have voltage at the top and then current and resistance at the bottom. So you have V, which is voltage, I, which is current, and R, which is resistance. The reason people draw it this way is because you can always calculate one of these if you know the other two. So for example, if you have both current and resistance and you want to know the voltage, you can just multiply current times resistance. So you can do voltage equals I times R. And this here is just showing you that you can like multiply them, right? And then if you have like voltage and resistance and you want to know the current, you can do V over R. So you can do I equals V over R like this. And then similarly, if you want to find the resistance and you have the current and voltage, you can calculate it by doing V over I, or voltage over current. So you can always calculate any of these if you have two knowns.
Yeah.
So this is actually how the multimeter works. The multimeter knows Ohm's law, and it essentially is able to calculate resistance because it knows the amount of current. It's using a really, really tiny, what's called a constant current source. And that means it's essentially having to vary the voltage in order to maintain that same constant current. But it's able to, because of that, it's able to calculate the resistance of the circuit or of the component that you're measuring.
So there's resistance mode, and then
the other. You want to know what the other modes are?
Name.
Let's try
Yeah.
resistance mode
Okay,
first.
okay, sorry.
So right now you're measuring 2.43 kilo ohms. So that's actually probably a 2.4K resistor. That's about 1,000 ohms, 1 kilo ohm essentially. That's probably the value of that resistor.
So would this be the same as the one up here? Like because they're the same size, or
No.
doesn't necessarily mean that?
No, it doesn't necessarily. The size does not dictate the resistance in any way. The size does dictate how much like wattage it can take, if that makes sense. How much power, like we talked about before.
Yeah.
If it's voltage times current. So the smaller ones can only take so much power and the larger ones can take more.
Am I measuring the wrong thing on that one?
No, I think you just...
Is it 100?
100 kilo ohms, yeah.
Is that what it was up here? I thought it was 1.
Yeah, it is 1. That one was 1 kilo ohm.
Oh,
So it's
that's
not...
100. Wow, okay.
So it's 100 times the resistance of the one above.
Wow.
Yeah, so it really does not like matter. The size of it does not dictate whatsoever the value of the resistor. But what? The size doesn't matter? Is that why you're laughing? So mature, Elay.
I was really trying to hold it in.
The other reason this is showing larger than what it is because there's also what's called a tolerance on resistors. And so there'll be like, maybe 5% tolerance. This probably is within spec. So we're going to take one of these out first so that you're not like having to work around so much shit. We're going to work with one of those resistors up there that's like,
that one?
Like maybe even, I think there's like one here. This one is perfect right here. Okay, so just practice sort of grabbing the component with your tweezers. And the best way, you can start by trying to grab it that way. This can be nice to grab it this way with the bent tweezers when you're coming up and around a component. Like if I was trying to grab it from the big collection of components over where we were before, it's nice to go that way with your tweezers, with your bent tweezers, so that you're not like getting in the way of other components. But when there's a lot of space like that, you don't have a lot of like surface area of your tweezers touching the actual resistor. And it's really easy, especially with tiny ones, to like flick them across the room accidentally. So yes, you have the right idea. Doesn't that feel better?
Yeah.
Like, so you have more control over that component. So what she did, I don't know if you can show like the side of the tweezers.
At first I was like this.
She's going with the flat side of the tweezers touching the board. So doing it this way, it really helps. I mean, even then you could see if you grab too hard, it's gonna like, if you do that, what you just did, when the component is unsoldered, it is going like
and you want it to
nowhere.
the void.
Yeah, exactly.
To the fume extractor.
Yeah. So yeah, you really want to have like a light grip on these components, you do not need to press. They're super, super tiny, so you do not need to like press the tweezers super hard. Also, like the flux that we're going to use is going to be kind of like tacky. So you're going to be able to use the flux to your advantage to like pick it up even sometimes without like grabbing it with the tweezers, if that makes sense. Because the component's so small, it will just stick to your tweezers. So a lot of working with small components like this is getting really used to your tweezers and like having full control over the strength of the grip on your tweezers. So you can pull the fume extractor a little bit closer to the board and then grab the flux over there. That's that one. And when you squeeze that little handle, it's going to push flux out of the tube. So just put some flux on that component.
Oh, wow. That's much harder than I thought.
Yeah, this particular flux is that's plenty. Yeah, that's perfect. Cool. So, and you're going to be able to see what you're doing more when you start using the hot air. So grab the hot air station and turn it on. The airspeed knob, you could change that to about like, I usually for components this small will do like pretty low, like 30% airspeed. Because this could be unleaded solder on the board. It's going to melt at a higher melting temperature. So we need to compensate for the lower airspeed by turning up the temperature a little bit more. So I'll use like 400 Celsius to take this thing off. And we're also going to sort of preheat the area before just blasting it with 400.
I used it last time.
You did? Okay.
Yeah.
Oh, that's right, because you used it for the BGA rework.
Yeah.
If you guys are interested, I taught her how to do reballing in a separate video, so you can go watch that. I'll have a link for it in the description. But yeah, so you're going to want to hold it so that, it's straight up and down, the nozzle straight up and down. Perfect. Let's zoom in on the microscope again. So you're just going to sort of like hold it over the area. Yeah, and you can go a little bit closer, not crazy close yet, but just sort of like put some heat into the board. Yeah, good. Circular motions are good. So this is just gonna like preheat the area and make it easier for when you get closer and are actually trying to pull it off. So now you can take your tweezers and get a like comfortable grip.
Do I pull a little?
No, don't pull the component because it's small and you can rip the pads off. And you can actually rip the sides of the resistor off as well. So make sure you're in a comfortable position with your hand and make sure you anchor your hand a lot on the table.
Yeah,
so that
pretty anchored.
You feel like you have control over like how much pressure you're putting on the resistor.
Yeah.
Cool. Okay, and you're not grabbing the resistor too hard. It's just like just enough.
Yeah, I think so.
Good. Okay, so now you can move closer with the hot air, much closer, like almost touching it, but don't look at the screen. Look at the board to see how. Yeah, and now you can look at the screen. And eventually, you won't even have to pull because it's so small. It's going to just start moving and your hand's going to start moving with the resistor. So you don't have to like try pulling away from it. You can angle a little bit the hot air if you want to be able to see what you're doing. Yeah, that's perfect. So you can kind of be right up next to it and you should feel sort of when it starts to move. Don't do that because what's going to happen is like when you put that pressure, when it is liquefied, it's gone. Like it's gone forever, which is fine. This is not an important board.
Am I doing something wrong?
You're not necessarily doing something wrong. It may just be that the hot air is not hot enough and we have too low airspeed. So what you could do is you could either try... Oh, there it goes. So, yeah, good. It's off. So you can remove the hot air. It did take a little long, so if you wanted it to be quicker, you could increase the airspeed a little bit. But if you were worried about blowing the component away, we could probably have used 450 degrees Celsius instead of 400. But yeah, you can see it sort of like sticks to the tweezers with just the flux. So now we're going to try to put it back, which is going to be a little tricky. But what I'll usually do is with the flux on it, I won't like pinch the component and take it off and put it on the mat like by pinching it. I'll just do exactly what you're doing here and just like allow the flux to work with you and leave it stuck to your tweezers and just very carefully put your tweezers somewhere else on the bench where you're not going to disturb them. And remember that you have a resistor on your tweezers.
That's so small.
Yeah, it's really small. You just can't even see it really. So be very careful putting your tweezers down so it doesn't like fall off, but it's not a huge deal if it does. Okay, so now we're just going to prep the pads on the PCB. I would zoom in a bit more so you can really see what's going on.
The board is so warm.
Yeah, the board is warm. It's a small board, so it heats up really fast. So now you're just going to put a little bit of flux on the pads again, and we're going to mix leaded solder in with this, and then we're going to wick it to take the sort of mixture off. So that's probably fine for what we're trying to do right now. You don't really need a whole lot of flux, so that's good.
Yeah?
Yeah, that's okay. So you can rotate the tip of the iron so that the shiny part is like flat on the board, you know?
Like this?
Yeah, like that. Exactly, yeah. So it's going to like actually touch.
Should I avoid touching these?
You don't have to. They're test points, so it's not a huge deal as long as they're not like bridging and stuff like that. If you wanted to avoid touching those, you could have a smaller tip on your iron. But what we're gonna do is first you gotta put some solder on the iron tip.
Oh yeah.
So just grab your solder there. Yep. And,
Yeah.
and do it right up next to the heating extractor. And yeah.
More?
Yeah, just put like a glob on both sides of the knife tip. Yep, perfect. Cool. You can come back into the footprint there, and then you can just sort of look at the microscope.
Do I hold the board?
Yeah, you can if you want to like keep it stable. We can also put it in a board holder if it's annoying.
That's fine.
Okay, and just touch those 2 points and try to make them like shiny, if that makes sense. The solder is gonna like mix with them if you hold the iron at a like good enough angle. So there's not actually like a lot of like solder on the part that you're touching the board with right now. You want it to be more like this, if that makes sense, in relation to the there we go. So you can see some of that solder sticking to the little triangle on the left there. So try to so you've mixed a little bit in with the pads there. You can see how they change color a little bit. They're a bit shiny. This is a pretty large iron tip for what we're trying to do here, but it's fine. It's just that we're putting solder in other areas.
Do it this way?
Yeah, of course, yeah. You can totally change angles. Angles really help. Okay, and there is like no more flux there basically. So that's fine. Like it's just because there's no flux, it looks ugly. It's not your fault. I mean, and also because we're taking a long time to like tin the pads or to mix the solder in, essentially the solder on the iron tip is getting oxidized, which is all that black stuff. It's like burnt flux and stuff like that. Let's clean this with some Q-tips and alcohol. You can press hard to try to get all that crap off. You can see like all of the stuff above, and see all those little spots on the board, like above the like there. That's where you like touched the board with your iron. So you were touching there instead of on the pads. So it's hard to see with a digital microscope like this.
So did I damage the trace?
No, I mean not really. Like you can damage traces if you like press too hard, but all it's done is scraped a little bit of the solder mask, but not enough even for us to be able to see the copper. So it's not like it's going to cause an issue. So now let's wick that off. Yeah, you can cut a little bit of the wick with those ceramic scissors there. Yeah,
this much.
You could do a smaller amount. I would do just that's fine. It's okay. And you can use the ceramic tweezers too to hold the little bit of wick, which is the white ones. Yeah, and using these is just to prevent like the tweezers from being a heat sink essentially. And next, with your right hand, just grab the flux, and we're gonna apply some flux again to the pads. Good, perfect. And now take your iron and make sure there's like a little bit of solder on it. I think there is from when you tinned it before, which is good. I'm gonna turn up the temperature of the iron to about like 400 Celsius, which should help transfer.
Should I go this way?
Yeah, perfect. That's perfect right there.
Yeah.
And just align before you like commit to this. Line up your iron in a way that you feel like it's gonna be the most ideal. That looks pretty decent to me, and you can just drag over the points. Perfect. Pretty good. Try one more time over the. Okay, so now it's stuck to the. You can see like it's stuck to the board. So don't pull on it. You're gonna want to sort of heat this with your iron again, and don't pull around and stuff. Just allow the iron to heat the wick sufficiently, and it will start moving by itself unless we don't have enough heat going into the wick. So don't pull on it, because when you pull on it, you're just gonna rip the whole pad off. It's really small. So if this is not putting enough heat into the board, what we can do is we can do two things. Re-tin the iron a little bit. You can let go of the wick with your there you go, perfect. That's fine. If you are unable to do that, you can just let go of the wick and re-tin your iron. And right now you're gonna want to re-tin your iron anyways. So just put a little bit more solder on there.
Is it off?
It's not off. It might be oxidized a little bit. So you can clean it in the brass sponge thing. When the tip is oxidized, it just doesn't transfer heat. So you want it to be shiny. And when you have this much solder on your tip, it's going to saturate the wick quicker. So you're not gonna have too much. I think you put a little too much. Yeah, I would just clean it off and then put like a little dab on one side that you plan to use with the wick. And if you wanted to, you can also try wicking the solder off of that little triangle that you put solder on as well. It doesn't matter, but. And just before you do this, you see how a lot of your wick is over those test points that you're not necessarily trying to wick?
Yeah.
If you do that, what's going to probably happen is the wick is going to get stuck on those because they're big.
Oh, yeah.
Unless you apply enough heat to the wick. So I would just, that's great right there. Perfect. Ooh, yeah. You're stuck on probably on that triangle thing. Cool. Nice job. That's perfect. So you can clean the iron, tin it a little bit, and then you can put it back. So now you're gonna clean all that old flux off.
Do I use the same Q-tip?
Sure. And you'll notice that if you just use one side of the Q-tip, it's just kind of spread the flux around a little bit. So yeah, rotate it. There you go. That's going to really help to like actually pick up some of the flux instead of just spreading it around. Nice and clean. Now we want to tin that again with some leaded solder only. So we mixed the unleaded and leaded, took it off the board, and now we're going to only put leaded back on. So just clean it first.
Again?
Yeah, I clean it all the time, constantly. Apply a nice sized glob. Like the bigger amount of solder you put on the iron, the less precise you're going to be able to be, but the easier it's going to be to get the solder to touch the pads, if that makes sense. So now I would put some flux on the pads.
Can I put it there?
Yeah, you can if you don't want to use your left hand for the flux.
I'll try. Do you use the flux with your left hand?
Depends. You really have to learn to be ambidextrous a little bit when doing microsoldering. Cool, so you can see how like the larger blob of solder made it easier to like get the solder to actually touch the pads.
So
it's peaking like that because the flux is no longer on the pad. So I would just put more flux on. A lot of people are really picky about like the amount of flux you use. I just use a little bit more so that you don't have to deal with, you know, the flux spreading out in the wrong direction like that. I clean all the flux off anyways, so I don't really give a shit, to be honest.
I can hear you holding in some of your instructions the way you breathe.
No, I'm not. I have no instructions.
Okay.
You're doing great.
Oh, I
No, you're good.
did the triangle again.
Just whatever. Good. So you can see how it's like a little bit more shiny.
Yeah.
Oh, and honestly, one of the reasons you're having a lot of trouble is because I adjusted your temperature up for using the wick. Because with the wick, you have the wick between the board and your iron. But what's happening now is because we're using 400 degrees Celsius, the flux is like spreading out from the iron because it's so hot. If we just put it down to 375, you would probably have a lot more luck with that. But that looks great. That looks perfect. So you can clean it, tin it again, and put the iron away. By the way, this is good soldering iron tip care is just clean after every time you use it and tin it again before you put it away. You don't want your tip oxidizing.
Wait, we don't want to clean this before?
Yeah, we can clean it again. I was just trying to show people that
that I'm a good student. Is this worth a chemoite?
Yes, I was gonna say that, but yeah, I would, because of how much flux is on the board there, I would use a chemoite with a brush.
Those are big.
Yeah,
Do you fold them in half?
No, I just use the. You can if you want.
Do I go in or I go on this first?
So first, I'll usually like put the chemoite on top and then brush it a little bit on top just to try to soak up a little bit of the flux with the chemoite, but it's only gonna soak up so much. And now I'll directly put the brush on the area with the alcohol and then soak it up again. This is just what I do. You can whatever you want as long as the flux gets off.
I don't want anything. I don't know anything.
No, I just mean, like, I'm just saying that in general.
Oh, for
like,
all of the other people.
For anybody, like, there's not a correct way to clean, really. I have my preferences, but
Okay.
I guess there are ways of cleaning that are more effective, I would argue. But.
I feel like I'm just adding.
So the alcohol evaporates. If you want it to evaporate faster and you're annoyed with how much alcohol is there, you can use the hot air. Put the hot air on it.
Oh, yeah.
So it evaporates quicker. So when I'm cleaning, sometimes I'll just do that because you don't really want alcohol while you're soldering. It's just a quicker way to get things dry. Okay, so now, again, angles are really going to help you with like placing the component and holding it in a place that's comfortable. Rotate it back to when you were taking the component off, because that's the same way you're going to be holding your tweezers to put it back on. So this is one way that you can put on an O201 component, or any component for that matter that's like this sort of package. You could also, what we could have done is just tinned one side and sort of like use the soldering iron along with the tweezers to put one side of the component on and then apply solder to the other one. I find with O201 components that is really tedious. Really tiny components like O201 components that are this small. This method for soldering I find is the easiest because while you do run the risk of blowing the component away with too much airspeed, you can just adjust the airspeed down. When you're dealing with the soldering iron and tweezers and this super microscopic component, it's a lot easier to accidentally like get the component stuck on your soldering iron and now all of a sudden it's just burning the component or
Oh yeah.
So like I prefer
that would be easy to do.
It's very easy to do that. And then like half the time you're just going to end up losing the O201 component in the solder on the iron and you just can't find it. It's probably burnt. And I just don't bother with the soldering iron with components that small. You can, especially with like super small irons, you can solder them with irons. I just don't see the point unless you can't use hot air in the area for some reason or you don't want to. So cool. Let's put some more flux. Great, that's perfect. And now I recommend grabbing the other pair of tweezers as well, the straight
This
pair. Use both of your hands to line the component up, and then you can drop one and use the hot air. So I would use in your right hand the one with the component on it. Yeah. Don't squeeze your tweezers together. Just try to let the flux pull the component off of your tweezers, and if it doesn't work, then yeah, use the tip of your other pair of tweezers to just push it off onto the board. Yeah, perfect. Yeah, exactly like that. Yeah, and what you're doing is great. Small movements like that aren't like putting lots of pressure on the component or on the tweezers is ideal. So honestly, just leave it like that. That's perfect. The tacky flux that we're using is really nice because it holds the component in place, and we're going to be able to use the hot air. If we use a low enough airspeed, it shouldn't blow the component away. I would put the airspeed like back where we had it, like 20% airspeed or something like that. Obviously, if you use too high airspeed, it's just going to blow it away. If you use a little bit too high airspeed, it's going to like float, for lack of a better word. It might still do that even if we use no airspeed and just somehow heated the board. Just the heat alone, melting the flux, may move the component. So we're going to have to deal with that if that's the case. Ideally, we can heat this and it will just melt the solder on both of the pads and pull the component into place without having to touch it at all.
What temperature should I use?
I would use 400 for this because it's leaded solder. For the other one, I should have told you to use like 450 because of the low airspeed. That would have been easier and taken less time to remove it. Yeah, but because you'll see the difference with how long it takes. I would be ready with your tweezers in your right hand, but don't touch the component unless you need to. Let the hot air get up to temperature first, so you can see it's like climbing there. And especially with the lower airspeed, it takes a little bit longer to get up to temperature. And go from farther away to just sort of start melting the flux. And you're just going to very slowly move the hot air in closer and closer until you start to see the component like maybe move a little bit. There you go. And just stay there. You can move a little closer probably. Yeah, a little bit closer, a little bit closer. That should be okay. And just wait. And eventually what's going to happen is both of those pads are going to melt and the component's just going to kind of like pull itself onto the pads. And it may be that we have to like tap the component a little bit. I would wait a sec just to see if it's gonna melt. But it may be that the pads are melted and the component is just not gonna pull itself into place, in which case usually just tapping it like a tiny bit on the bottom in this case would be enough. You can see the solder next to it is melting, which is a mixture of the leaded and unleaded, I think, that you had on your iron. So probably, unless it's like a ground pad, which it totally could be, that other pad is probably melted and we just have to tap the resistor a tiny bit. It's going to be really easy to push it too much. And you're looking at the top part of your tweezers, which is not even anywhere close to the board. You'll be able to tell if it's close to the board, yeah, because it's in focus. And then, yeah, good. Small movements. Yeah, okay. So what's happening is because you're so focused with your tweezers, your hot air is not anywhere close to the component and it's not applying enough heat to the pads to melt the solder. So do your best. Yeah, you can see it's melted now. So just do your best to get it in place. Good. Nice. Keep poking it. Cool. Perfect. Okay, now just call it quits and let go of the hot air for a sec. Because the component is soldered down, you really don't have to worry about it blowing away anymore because the surface tension of the solder is going to keep it in place. So you can actually boost your airspeed a good amount.
How much?
I would just say to like 40%. Yeah. And then you can leave the temperature, that's fine because the higher airspeed is just going to melt it quicker. But put more flux now because it took a little time to move things around. Your flux is basically gone and you want to get a better joint so you can reapply flux and then reflow this now. And again, you don't have to worry about it blowing away, so you can go right up next to it and just reflow it and watch the component if you can, because you'll probably see it sort of pull itself into place a little bit and you're not actually over the component. There you go. Yeah, like that. And just hold it there. You don't have to go any closer really. And you're gonna be able to see the solder next to it and on either side of it melt.
Well, it did move a little bit.
Oh, you watched it move?
Yeah.
I didn't see it, so probably it did.
Okay.
So it's good now. There you go. First try. You can see it's like very finicky because it's so small, but it's not too bad, right?
No, that wasn't too bad.
So just with the right tweezers and the right use of your hot air station, and also replacing the solder with leaded solder, really makes it not too bad, I would say, to solder components this small. I know. Yeah, clean it. Go ahead and clean it. It's actually better to clean it when it's warm like this because the flux is more liquefied. So feel free to brush and everything.
The board is so warm.
Yeah, these smaller switchboards heat up really quick. And it's a perfect time to clean because it makes it easier to clean.
I don't know, that looks clean to me. Is it clean?
There's some, you can see there's some flux like, here, I'll point with the tweezers. There's flux like here. You see that?
Yeah.
So you can try to like use some alcohol and scrub around there. And then you can try to soak it all up with the Wicking wipe. And just keep moving, because right now this is not going to do much. You want it to soak from the dry spots on the Wicking wipe. Yeah. Cool. And a lot of that is probably just going to be alcohol, right? Yeah, that's pretty clean now. Nice. And you have your component there still.
I do. And a triangle as a bonus.
And the triangle is tinned as a bonus. So you can see like that wasn't horrible because it was just sort of like out in the open.
Yeah.
But when you're doing one that's closer to things,
yeah,
it's a little bit worse.
Would be annoying.
Because what happens is you end up like pushing components around if you're not making really tiny movements. But what helps with that is just anchoring your hands and being very intentional with every single movement you make on your tweezers. It's the exact same process. She's cleaning the tweezers with the brush.
Is it not a good idea?
No, it's fine. It's funny though. You just did that out of your own. You just wanted to do that. Like,
no, there's
actually,
flux on them.
There is flux on them, and actually, what I've been doing recently is taking the little sponges, and they're really satisfying if you just dip the tweezers in the alcohol. You could also dip the sponge too, but I just dip the tweezers and then just stab it a bunch. Yeah,
nice
just stab it over and over, and then it really does a great job of cleaning the tweezers. Yeah.
You didn't like my brush method?
Your brush method was fine, and I'm sure it worked great. This is more satisfying though.
I don't know. Did you try the other one?
I guess I did not try it. Maybe I'll give it a shot.
The brush is satisfying too.
Was it?
Yeah.
Which one is more satisfying?
I like the sound of this. Well, was that the end of my lesson?
It can be if you want.
Where do you...
I've started to use this little spinny thing for it, so I put them here. I used to stab them into my mat, but since I got a new mat, I just started using this thing.
Very nice.
And I finally put a big enough hole in here with the Dremel to fit the
That works.
mini wear screwdriver, which I'm really happy with. It's perfect.
I'll stop playing with her toys.
Well, thank you, Elay, for letting me use you for another video.
Thank you, NanoFix, for the lesson.
If there's anything else you guys want me to teach my wife how to do, let me know, and we'll make another video. But I appreciate you guys for watching, and I will see you in the next video. Peace.